Okay, now we're on YouTube. Tracy, the slide went away. I don't know if that was intentional.
Sorry, I thought I heard that Christy wanted to check something else. Should I go ahead and put it back up?
You can put it back, sorry.
Okay.
Thanks, Tracy. Hi, everyone. Thanks for joining. We'll get started in a few minutes.
Okay, that seems good.
All right, it's 11 o'clock Mountain. Christy, you ready to get started?
Yeah.
Okay, now we're recording the meeting,
Yes.
so you should see a little pop-up. Okay, welcome everyone. Welcome to the CGD Seminar Series. Thanks for joining us. Just a reminder of our Zoom ground rules. Please remember to stay muted, cameras off. During the Q&A, you'll have an opportunity to either type your questions in the chat or use the raise hand feature, and feel free to then unmute and turn your cameras on so we can have an interactive discussion. And please remember to share the air during the discussion. So I'm very happy to introduce our seminar speaker today, Dr. Cristian Proistosescu. Cristi is an assistant professor in the Department of Atmospheric Sciences and the Department of Geology at the University of Illinois at Urbana-Champaign. He received his bachelor's in physics from Princeton University in 2009 and his PhD in Earth and Planetary Sciences from Harvard University in 2017. He was a postdoctoral fellow at the Joint Institute for the Study of Atmosphere and Ocean, or JASEO, at the University of Washington before joining the University of Illinois in 2020. There he leads the Climate Dynamics and Data Science Group, where their research areas span coupled climate dynamics, statistics, climate sensitivity, clouds and radiative feedbacks, and paleoclimate. Today, he will speak about the fly in the ointment. Coupled climate models fail to simulate observed warming patterns, resulting in weakened constraints on future warming. Cristi, the floor is yours.
Hello, everybody. Okay, let's start by sharing my presentation. Okay. Can everybody see this? Can everybody see the pointer? Looks full screen, looks good.
Yes, all good.
Okay. Thanks, everybody. Thank you so much, Katie and Tracy and Ayla for inviting me. It's a real pleasure to give this talk at NCAR. And this is new work. It's very much work in progress. It's the first time I'm talking about it. So hopefully this makes sense. This talk is more of a question than a comment. I'm very confused about these issues, and I thought I'd spread the confusion around in the hope that maybe somebody makes sense of this. And what I'm going to talk about today is the fact that coupled climate models fail to simulate observed warming pattern, which weakens constraints on future warming. This could also be called historical warming does not rule out high climate sensitivity. This work is funded by NOAA under the Program for Modeling, Analysis, Prediction, and Projections, part of their task force on constraining climate sensitivity. And this is work done with a lot of collaborators that have contributed ideas, simulations, analysis, and so on. Yue Dong, Kyle Armour, Rob Wills, and David Battisti at University of Washington, Malte Stucker at Hawaii, Tim Andrews at the UK Met Office. So let's start with defining climate sensitivity. So equilibrium climate sensitivity, or ECS, is defined as the equilibrium change in Earth's global mean surface temperature in response to a doubling of atmospheric carbon dioxide relative to pre-industrial conditions. This is the IPCC definitions. It's ostensibly the simplest possible metric of the climate system's response to increasing greenhouse gases. It's long-term equilibrium, it's global mean, but it turns out that it is actually informative of warming on timescales of human interest. So this is from the recent World Climate Research Program, WCRP report on climate sensitivity, Sherwood Webb et al. 2020. And here in this figure, we show that models with high ECS also tend to warm more by the end of the century. So it's also a good predictor of near-term warming. It turns out it's also a good predictor of regional warming over the next 100 years, though I don't show that. So this is all to say ECS is actually an important metric, both intrinsically and for purposes of future climate predictions. So what are we going to do in this talk? This is a roadmap to the talk. We're first going to motivate it. We're going to talk about constraining the upper bound of climate sensitivity. And the word that's going to come up in that is the pattern effect. So then we're going to review the physics of this pattern effect. And we're going to go into newer results. And I'm going to show how SST patterns differ between models and observations, changes in circulation and changes in radiative feedbacks, before talking about implications for climate sensitivity. So ECS, the range of equilibrium climate sensitivity. The first estimate of climate sensitivity dates from the Charney report in 1979, and they give a likely range of about 1.5 to 4.5 degrees for a doubling of CO2. 5 IPCC reports later, there's not much of a dent in this range, with transient exception in AR4. The likely range is still 1.5 to 4.5 degrees. There's recently some progress been made, again, in this WCRP assessment that I mentioned, where we said at the end that the likely range of climate sensitivity is actually narrower. We were able to narrow this down to something like 2.6 to 3.9 degrees for a doubling of CO2, with broader uncertainties for the 5% to 95% range. However, even this comes with caveats, especially for high climate sensitivity. And here's one caveat. A lot of the constraints in this assessment, especially on the high end, come from paleoclimate. If we ignore paleoclimate, or if we believe that there are still big caveats with paleoclimate constraints, then the modern record, process understanding and observations of historical energy budget changes, don't really constrain the upper bound. The likely range is still about 4.6 degrees, and 95% range is over 6 degrees. And here's more reason to worry. There's troubling signs from CMIP6. This is the equilibrium climate sensitivity in CMIP6 models. This, Russian SPEC and Wolfpack, I think comes from Gavin Schmidt or Mark Zelinka, I forgot who named them this way. But there are a number of models in CMIP6 that exhibit very high climate sensitivity, above 4 degrees or 4 kelvins for a doubling of CO2. This is a tweet from Mark where he breaks down the southern hemisphere, 30 degree to 60 degrees south, shortwave low cloud feedback in these models. And what I want you to notice is that the models with high climate sensitivity, the purple models, tend to have strong low cloud feedback in the Southern Ocean. That's not the only way get high climate sensitivity. You can get high climate sensitivity like the weak Southern Ocean cloud feedback, but all the models that have a strong Southern Ocean cloud feedback, except this one, tend to have high climate sensitivity. And that's worrisome because we think that actually those models do a better representation of processes in the Southern Ocean. So it's more complicated, but one way to think about it is models that have improved processes in the Southern Ocean clouds have higher ECS. So does that mean that we should trust them more? Well, I don't know if we should, but this is reason to worry, I think. It means that we have weak constraints on the upper bound of climate sensitivity from process and observations. From process, just that clouds are hard. From observations in the WCRP report, we mentioned something about how uncertainty in the pattern effect precludes constraining the upper bound. And more reason to worry is that a lot of latest generation climate models exhibit high climate sensitivity. So if you've been following these, the CMIP6 models, there is one reason for hope. And that relates to this question of whether historical warming informs future warming. So these are CMIP6 historical climate simulations. For models that have more than one historical simulations, I've taken the Ensemble average. And this is historical warming relative to a baseline of 1880 to 1900. And you can see that there isn't really that much relation. There's a number of climate sensitivity models that don't warm a lot, and there's models with fairly low climate sensitivity, nonetheless warm a fair amount over the historical record. And we think that one reason why there's not a strong relationship here is because of the effects of anthropogenic aerosols, especially in the second part of the 20th century. However, if we look at more recent warming, there is a relation. There were a set of 3 papers that came out within the last year and a half. Diego Jimenez de la Cuesta and Torsten Moritzen, Kasia Tokarska, and Femke Neisse, that make the point that if you look at recent warming relative to 1980, there does appear to be a strong relation between the equilibrium climate sensitivity, denoted by the color, and the warming over the last, about 40 years. Models with low climate sensitivity tend to not warm as much. Models with high climate sensitivity tend to warm more. So the recent warming suggests that this suggests that you can constrain equilibrium climate sensitivity from recent warming trends. This is a schematic of that. The x-axis is temperature change since 1979. On the y-axis is the equilibrium climate sensitivity, where I've plotted, for models with more than one historical simulation, I've plotted the Ensemble mean. So there does appear to be a relation between recent warming and ECS. I've pasted that histogram of CMIP6 models. So these are the high climate sensitivity Wolfpack models here. And the idea is that you can find a relation between recent warming and ECS. this is a schematic. These papers have done the actual statistics. You can look at what the recent trends are over this interval, and you can say, well, the ones that don't fall within this trend, we can discount. So then you can make an estimate of climate sensitivity as being most consistent with the climate sensitivity of recent record. There's some issues with this, which is that it ignores models that outliers that nonetheless can have high ECS and low recent warming. But the idea is that recent warming can inform on climate sensitivity, and that the most consistent models are the models with low climate sensitivity. These are the actual figures from those 3 papers. Each of them plots, some metric of warming over the recent record, with various definitions versus equilibrium climate sensitivity in CMIP5, and then more recently in both CMIP5 and CMIP6, there is a strong relationship and it suggests a low climate sensitivity. So does this mean we're out of the woods when it comes to high climate sensitivity? Well, not exactly. These papers come with caveats. This is actually from the abstract of the Jimenez de la Cuesta and Moritz in 2019. And in the abstract, they say that for equilibrium climate sensitivity, we obtain a best estimate of 2.83 with a range of 1.72 to 4.12 kelvins. Contingent on the temporary pattern effects exhibited by climate models. So there is this caveat, and it's right up front in these emergent constraint studies. This is what these approaches are called. They're contingent on the pattern effects exhibited by climate models. Then they go on to say, if the real world surface temperature pattern effects are substantially stronger, then the upper bound equilibrium sensitivity may be higher than found here. If the real world surface temperature pattern effects are substantially stronger. Okay, so are they? That's what we're going to spend the rest of the talk figuring out. Because if they are, then these emergent constraints may not necessarily hold, and the upper bound of climate sensitivity may not be well constrained. Okay, so I've brought up this pattern effect at least twice now. So what is it? What is it talking about? I'm going to spend the next couple of slides reviewing the physics behind this notion of a pattern effect. To do that, let's start with a simple view of Earth's energy budget. If we apply radiative forcing, such as increasing greenhouse gases, we have an energy input into the climate system. This is called the radiative forcing. These slides are taken straight out of my climate dynamics class that I'm teaching, this particular slide. And what happens is that the temperature increases. The overline denotes global mean values. So the temperature is going to increase. This is going to lead to radiative damping and net heat uptake by the system, delta Q. I can think of it as the rate of increase in the internal energy of the climate system. Where the radiative damping or radiative response is just black body radiation. You increase temperature, you radiate out more, mediated by atmospheric feedbacks. And the key notion here is this notion of a radiative feedback. This lambda, the efficiency of radiative damping, which links changes in global mean surface temperature to changes in the global mean radiative response. Okay, so where does the pattern effect come in? Well, this lambda links global mean surface temperature to global mean radiation. This is a figure of surface temperature trends divided by global mean surface temperature in NOAA ERSS theory construction 1979 to 2020. So this is normalized by the global mean change, so it represents just the pattern of warming. The average of this map should be somewhere close to 1. And then by comparison, here is what the long-term warming pattern looks like, taken as the trend over the first 150 years in SIMIP6 abrupt quadrupling simulations. Notice it's very different. It's a lot more uniform compared to the recent warming pattern. So the question arises, do we really expect to have the same radiative feedback? Do we expect for the same amount of warming, if the patterns are so different, do we expect the radiation to be the same? And the answer should be pretty obviously no. Okay, so how do we move forward then? Well, we tailor expand. So if we think of what that lambda means, what that net radiative feedback means, that net radiative feedback represents the relationship between global mean radiative response and global mean surface temperature. But if radiation isn't just controlled by global mean surface temperature, then we need a more refined view of this feedback. So we can tailor expand by saying that global mean radiation actually depends on temperature at every location times how much regional temperature changes. If we do that, then we can normalize by the global mean surface temperature. And what we find is that this net feedback lambda is actually a function of how radiation depends on local temperature change. You can think of this as the atmospheric radiative response to the surface pattern times what the pattern of warming is. Right? So the net feedback depends on this, on how the atmosphere responds to surface pattern, to surface temperature, and what the pattern of surface temperature is. So how can we get some information on this atmospheric pattern, on this radiative response pattern? Right? How does radiation depend on the pattern of warming? To do that, we can use Green's functions. So we can take a model, we prescribe observed sea surface temperatures underneath an atmospheric model, such as CAM4 or CAM5. Select a patch where we increase the sea surface temperature, that only in that patch. So we impose a change in local sea surface temperature. Can people still hear me?
Yes, we can still hear you. It's cutting out a little bit, but if it helps, you could turn your video off.
Okay, let me do that. Let me try to do that.
It's actually okay now, Christy. So if you want to keep going, I'll let you know if it gets worse.
Okay, thank you. I just got a notice that my internet connection is unstable. Okay, so where were we? Okay, so we take the pattern of sea surface temperatures. We impose a regional anomaly in sea surface temperature for the global radiative response. And we can approximate that then as this relationship between global radiative response and regional surface temperature changes, in particular sea surface temperature changes. If we do that, this is what this map looks like. This is what is called the Green's function because it's obtained by imposing these delta function type perturbations. This shows the dependency of global mean radiation on local warming. So if we impose warming in the here in the West Pacific warm pool, what this means is that we get a very strong negative radiative response. That's energy out of the climate system. Energy radiation doesn't get out locally, it get out everywhere. But the dark blue here means that if we warm in the West Pacific, we radiate out a lot. Conversely, if we warm in the East Pacific, we actually get more energy into the climate system. So it'd be a local runaway. You actually get a local runaway positive feedback. This is from CAM5. Chen Zhu ran this simulation in 2017. We ran a similar simulation with CAM4 in 2019. The details look a little different, but the overall pattern looks the same for both CAM4 and CAM5. and we have no idea what it might look like in other models. So it's worth trying to understand a bit where this pattern comes from. And to do that, we have to think a bit about tropical climate dynamics. So this is a map of tropical sea surface temperatures. And here I'm going to show a schematic, a slice through this, where we're going to look at the vertical profile above the warm pool and above subtropics. So as you go from warm pool to subtropics, imagining from the warm pool into subtropical colder regions here in the East Pacific. In the West Pacific warm pool, we have deep convection, we have a region of ascent, we have convection, we have a lot of precipitation here in the West Pacific. These thermally direct Hadley and Walker circulations with ascent over the warmest SSTs and descent over colder SSTs. Temperature profile in the West Pacific is set by a moist adiabat lapse rate, which links the tropospheric temperature in the west to the sea surface temperature. According to the weak temperature gradient approximation, this essentially sets the free tropospheric temperature profile everywhere in this. So the free tropospheric temperature in the East Pacific is still going to be linked through the WTG and moist adiabat to the SSTs in the West Pacific. And then in the East Pacific, the upper level temperature is set by the weak temperature gradient and the moist adiabat in the West Pacific, but the lower level temperature is tied to the cold sea surface temperatures. So you end up with this trade inversion in the temperature profile in the West Pacific. You can measure this using a metric called estimated inversion strength. Look at a map of it, then you find what you expect. You have these strong inversions in the East Pacific for regions of cold sea surface temperatures. And these regions of strong inversions tend to be associated with low-level clouds, with cloud-topped boundary layers, which live at the top of this of the boundary layers over the cold SST. So this is a simple view of the tropical climate circulation. In a review, Bjorn Stevens calls it a parochial view of tropical circulation in clouds, but it suffices for our purposes. Okay, so with this in mind, let's think of what happens when we increase temperatures in the West Pacific warm pool. So if we impose a temperature perturbation in the Pacific warm pool here over the warmest temperatures, we increase temperature here. The atmospheric temperature is tied to a moist adiabat to the surface temperature. So the free tropospheric temperature is going to increase in the West Pacific. Due to the weak temperature gradient, it's going to increase in the East Pacific. That's going to strengthen the trade inversion. It's going to increase EIS, and you end up with more low clouds. Because you warm the free troposphere, you end up with a net negative lapse rate water vapor feedback because you warm the free troposphere. So you end up radiating a lot in the long wave throughout the tropics. And because you've increased the strength of the inversion in the clouds, you also reflect more radiation out. So you get negative, you basically get a negative feedback. And that explains pattern in the Green's function where warming in the West Pacific leads to more outgoing radiation in both the long wave and the short wave. Conversely, if you increase temperatures in the East Pacific where sea surface temperatures are cold, you're mostly just changing the temperature here in the East Pacific, in the low level temperature, which weakens the trade inversion and you end up with fewer low clouds. This overall leads to a positive lapse rate vapor feedback, as well as a positive shortwave feedback. So if you warm in the East Pacific, you end up with more energy coming into the climate system, more radiation coming into the climate system. Okay, so to summarize this this pattern effect, we have this dependence of radiation on the temperature warming pattern, where warming the warmer SSTs leads to more negative feedbacks, while warming the cold sea surface temperatures leads to more positive feedbacks. And in order to understand the net feedback, to multiply this Green's function by the warming pattern, and the historical warming pattern has a lot of warming in the West Pacific, and where you have a negative feedback, and it actually has cooling in the East Pacific, where you have a positive feedback. Overall, the historical warming pattern should lead to more negative feedbacks. So the lambda historical is more negative than the rate by the warming pattern from models. Okay, so we've reviewed the physics of the pattern effect. And the reason I wanted to do that before looking at SST patterns is because it's going to guide us. It's going to tell us what are we looking for in the SST patterns. So how do observed and modeled sea surface temperature patterns compare, and how do they project onto radiative feedbacks? These are the sea surface temperature patterns in models and observations. On the left, we have the trends 1979 to 2020 from NOAA ERSSTs. Again, this is a normalized warming pattern. Average should be 1. And to the right, we have CMIP6 historical runs, which go to 2014, and then extended with SSP 245. So this is an average across 40 models, a total of 303 historical plus SSP runs, and they look very different. This is essentially uniform. If anything, there's a specific. The observations have the opposite pattern, especially in the tropical Pacific. Okay, so that's the ensemble mean. Do any runs match the observed pattern? Well, what metric do we want to use? We're interested in the impact of radiative feedbacks, and we said that what matters most for radiative feedbacks is what's happening here in the tropical Pacific. So here's one metric we could use. We could use this metric gamma, which is the ratio of warming in the warmest SSTs versus warming in the tropical, versus tropical average sea surface temperature warming. We shown in 2019, Yue Dong and others show that this ratio explains the time dependence of feedbacks in models. And then Stefan Fuglistaller shows that this metric explains variations in the satellite record. Well, in Dong 2019, we actually use global mean. We actually use warm pool temperature over global mean SSTs, but I kind of like Stefan's SST, warm SSTs versus tropical SSTs. Part of what's nice about this metric is it allows for changes in the mean state between models and observations. This is what the warmest 30% of SSTs look like in NOAA ERSST. This is what they look like in CSM2. So this is a model-dependent metric that allows for differences in the mean state. Okay, so let's look at how the ensembles do. These are those 300 plus ensemble members. The x-axis is the ensemble member. Y-axis is this ratio gamma, and here are the observations. So the observations show that the warmest SSTs have been warming faster than the tropical average SSTs, and that's not really the case in any of the models. This is the CSM large ensemble. So I guess this is CMIP6 plus CSM1. There's CSM2 somewhere in here. I forgot to label it. If we look at a histogram of this, what we find is that there's only one ensemble member from my rock, I believe, where the warm pool warms as fast as in the observations. Everywhere else, the warm pool doesn't warm nearly as fast compared to the tropical average. Okay, so that was 1979 to 2020. However, not all historical model runs have an associated SSP run or have as many runs. So if we only want to look at CMIP6 historical runs without extending them, we have to limit ourselves to 1979, 2014. If we do that, we have 58 models, 534 runs, and the pattern is, the discrepancy is even more amplified. There's even more of a discrepancy between West Pacific warming and East Pacific warming. We can do the same histogram. So this is now the ratio of warm pool warming, or of warming in the warmest SSTs. Some of them are in the ITCZ. This is the tropical average SST. And actually over 1979 to 2014, not a single model run that captures this ratio. Okay, so besides SSTs, what can we look at? Well, we can look at Walker circulation trends. A increase in sea surface temperatures in the West Pacific warm pool should also accelerate the Walker cell. So accelerated warm pool warming relative to tropical average warming should accelerate the Walker circulation. This is sea level pressure from ERA5, and we can define a Walker circulation index as the difference in sea level pressure between these two boxes. Part of what's nice about looking at sea level pressure is that it's related to tropical SSTs and the pattern effect, but there's independent observations of sea level pressure. So it's not as sensitive to your choice of, say, the sea surface temperature data set, which Lewis and Moritzen showed that it can introduce biases in the pattern effect. If we look at CMIP6 AMIP simulations, so these are atmospheric model simulations forced with observed sea surface temperature trends, these models are able to reproduce the overall pattern. The coupled models, not so much. So the atmospheric models seem to do okay given the right boundary conditions, but the coupled model less so. Now I say, well, what if it's natural variability again? This is what it looks like if we plot the histograms. In orange, the coupled simulations, in the AMIP simulations, and in olive, I guess, is this color, is the observations from ERA5. So not a single model captures the strengthening of the Walker cell over the 1979-2014 interval. This was also shown, in CSM1 by Zhao and Allen in 2019. This is now for the full CMIP6 historical runs. We can also look at estimated inversion strength. Remember, we said that accelerated warm pool should lead to a strengthening of the trade inversion. Again, we have independent observations of temperature profiles. These are trends in EIS from ERA5. These are trends in EIS from AMIP simulations, so forced with with observed sea surface temperatures. And this is the CMIP6 mean and over coupled historical simulations. And now if we take the average trend over these boxes, and we do the same histogram, again, we find that the observations tend to lie basically outside of the range generated by the large ensembles, with one or two, actually more like 5, I guess, ensemble members that are able to generate a strengthening of the inversion that is consistent with the observations. But by and large, all of these metrics tend to lie at the edge or outside the full ensemble range in CMIP6. Okay, but is there a bias in the feedbacks? So we've talked about SST patterns, we've talked about Walker circulation, EIS, but what about the radiative feedbacks? So to do that, again, we can look at coupled models versus AMIP simulations with prescribed sea surface temperature and sea ice concentrations. But we can only do that in a couple of models. So what we're interested in is this radiative damping. And to do that, we need to know the radiative forcing and the net heat uptake. The net heat uptake is standard output in CMIP. It's just the top of the atmosphere energy imbalance. But only 8 models have so far run the required RFMIP radiative feedback model simulation that allows us to estimate trend in radiative forcing. In addition, we ran it for CSM1, or I should say Malte Stucker ran for CSM1. So we have 8 SMIP6 models plus CSM1. We've got 9 models where we can actually diagnose the radiative response. And if we do that, this is what it looks like. This is the net radiative response divided by global mean surface temperature in these 9 CMIPs plus CSM1 AMIP runs versus the SMIP6 historical runs where we have 9 models and 231 runs. So when forced with observed SSTs, we have much more negative radiative feedbacks, primarily associated with this with these East Pacific. These are East Pacific, primarily low cloud feedbacks in the East Pacific. We can again look at the full ensemble range. So this is now the net radiative feedback in coupled historical simulations versus simulations with forced observed SSTs, trends over 1979 to 2014. And consistently in all the models, the radiative feedback from observed SSTs is different, is much more negative than the one from the coupled models. And remember, this is the same atmospheric, same cloud physics, same cloud microphysics, same club parametrization, same everything. It's just the sea surface temperature patterns that's different. And much more negative radiative feedbacks. And this holds true basically in all the models, in all 9 of these models for which you can diagnose this. If we look at the equilibrium feedback, it's much closer to the ones from historical simulations. And we can look at the strength of the pattern effect. You can define this as the change in feedback between historical and equilibrium. It's negative across the border. So coupled historical simulations also have more negative feedbacks than equilibrium. But if you drive the models with the observed sea surface temperature patterns, you end up with much more negative radiative feedbacks. And that's a problem. Okay, so if you've fallen asleep, this is a good time to wake up. All I've talked about so far can be summarized in one slide. So here are the salient points from what I've talked about so far. Observations show that warm pool sea surface temperatures have warmed the fastest, at least in the tropics, I should say, or have warmed faster than the tropical average. And coupled models fail to reproduce this pattern, even when accounting for large ensembles. This accelerated warming in the West leads to a warming of the free troposphere. Actually, there's a paper by Steve Pochedli in PNAS that shows specifically the free tropospheric warming, came on the last 2. There's acceleration of the Walker circulation, strengthening of the inversion, increased cloudiness, all of them essentially lying outside of the range generated by the ensembles. And critically, these observed sea surface temperature patterns drive more negative radiative feedbacks. Here I'm just showing CSM1. So the strength of that pattern effect seems to be much stronger in observations relative to coupled simulations, which was precisely the caveat that Diego and Torsten warned us about in their 2019 Emergent constraint paper. This is exactly the type of behavior that they warned could weaken the constraints on high climate sensitivity. Okay, so hopefully everybody's on board with this so far. So now, for the last 15 minutes, I'm going to talk about implications for climate sensitivity. Does this suggest a low or a high climate sensitivity? Well, it depends on what you think the future holds. This is again the observed warming trends versus the warming trends in abrupt. That should be abrupt, obviously, in abrupt 4 times CO2 simulations. So the question is, do we expect warming trends to eventually asymptote to the warming patterns in abrupt quadrupling simulations? Do we trust the long-term warming pattern? Well, maybe we do. This pattern in the observations sure does look a lot like the IPO. This is an index of the interdecadal Pacific oscillation based on warming in the gyres and warming in the East Pacific. And what we notice is that there's been a negative trend in the IPO over this interval, 1979 to 2014. And even if you go back, if you extend it to 2020, the overall trend in the IPO index is still negative. So if we think that this is just natural variability and it's asymptote to the long-term pattern in the models, then we have a problem. And let's see what that problem is. So if we go back to this view of Earth's energy budget, we have Earth's energy balance forcing plus damping plus heat uptake must equal 0. We've defined this net radiative feedback tying global mean radiative response to global mean surface temperature. We can also define a heat uptake efficiency tying global mean temperature anomalies to global mean heat uptake, at least in the transient, while the deep ocean is still cold, hasn't warmed up. And if we do that, then we can define transient warming as being equal to historical forcing divided by the radiative feedback and the heat uptake efficiency. Whereas in equilibrium, the heat uptake goes to 0 and the will be a function of by the radiative, where you take into account the difference between the historical feedback and the equilibrium feedback. And this is the held 2010 model. Right, so you have taken into account this difference, which is due to the pattern of the change in feedback due to the change in warming pattern. So let's review this relation between recent warming and ECS, where we have, again, I've showed this figure before. On the x-axis is a warming trend over 1979-2014 versus a climate sensitivity in historical model runs. And let's think about what this relationship really entails. So let's talk about emergent constraints, which are what constraints are. You look at historical warming, which is unobservable, and you try to constrain an unobservable quantity such as climate sensitivity. Now there's a truth somewhere in here where the observed sea surface temperature trends or surface temperature, sea surface temperature trends relate to a true climate sensitivity. And if we think of this held 2010 model, the historical warming is going to be a function of CO2 forcing and other forcing, primarily aerosols, divided by the equilibrium feedback, the importance of the pattern effect, and the efficiency of ocean heat uptake, whereas ECS is the greenhouse gas, the CO2 forcing divided by the equilibrium feedback. We don't actually know what ECS is, that's to find out. All we know is where the observations fall. And we have these GCMs, which don't fall quite and we don't know what their ECS is either. But, and here is the key assumption of emergent constraints. There's the assumption that if you have uncertainty in the GCMs, the GCMs are wrong in the right way. That if you have errors in your climate models, they impact both your observable historical warming and climate sensitivity. And that's clearly the key for the equilibrium feedback and the forcing associated with CO2. If you have an error in either of them, it should project onto both. So then your model spread should be a line in this space. And the key idea between emergent constraints is you don't need to constrain these terms individually. You can't. We don't know what the equilibrium feedback is. We don't know what the strength of the pattern effect is. We don't know these terms individually. Only need to constrain the observable temperature. With the GCMs, you trust the GCMs to reproduce the relation between the different parameters. This is the emergent part where the models reproduce the emergent relationships. However, here's the caveat comes in. What happens if you have errors in your models that affect historical warming, but not equilibrium climate sensitivity? So things like aerosol forcing, of heat uptake, and this pattern effect, at least if we think this is part of variability and it doesn't matter equilibrium, all of these things are going to introduce error on your x-axis. That's okay, as long as these errors don't have a consistent direction. Then you're okay. Then all this does, it adds some noise. Well, and some regression dilution, but I'm not going to go into that. However, what happens if you have a consistent error, if you have a biased error, which is the case for the pattern effect with respect to observations, right? We've said that basically all of the coupled runs, which is what blue ones represent, have a stronger pattern, have a less negative pattern effect than in the observation. So that should make models run hot over the recent interval. And if this is a consistent bias, you can still end up with a tight emergent constraint. But now if you're using this biased emergent constraint, you're going to infer a climate sensitivity that is biased low relative to the true climate sensitivity. So this is that caveat that Diego and Torsten warned us about. If there is a consistent error in the pattern effect, then your inferred climate sensitivity might be low compared to the true climate sensitivity. Let's see if we can actually estimate the magnitude of that. So for those 9 models where we have diagnosed the radiative feedbacks over the historical record, we have this relation between historical warming and climate sensitivity. And what we can do is we can correct for the change for the pattern effect by diagnosing gamma, that's the heat uptake efficiency, and then replacing the radiative feedback, the historical radiative feedback from coupled historical simulations with that from AMIP. And that this is what the correction looks like. So given the observed sea surface temperature pattern, even high climate sensitivity models could reproduce historical warming. Right? Same climate sensitivity, same cloud physics, same microphysics, give it the right SST pattern and it's not going to warm much over the historical record. Once you do this correction, you basically lose any ability to rule out high climate sensitivity. Okay, well, what about the other models? We only have 9 models for which we can actually make this correction for which we can diagnose the feedbacks. There's 58 models so far in the SMIP6 historical ensemble. Well, to paraphrase the inimitable Kate Marvel, all I want for Christmas is more RFMIP, PI-CLIM, HISTOL simulations. That might seem like a very specific ask of Santa, but that would actually really help us a lot in understanding just how important these SST patterns are. What we can do, though, as a poor man's correction, let's assume that this is natural variability. So instead of just plotting the ensemble mean for recent warming versus ECS, let's plot all of the ensemble runs. There's 534 runs across 58 models. And if it is natural variability, let's just take the 5th percentile right? So if it is natural variability, you have to take into account the phase of natural variability. If we think that the phase of natural variability biases models to low, then let's do the emergent constraint on the 5th percentile. If we do that, all of a sudden, this constraint weakens. You have much models with high ECS that are consistent with the observations. It doesn't fully address the issue. That's probably because, as we've said, the observations actually lie outside of the model range. But it goes, it does help. Okay, so let's review this. Observed sea surface temperature patterns drive more negative radiative feedbacks. And given the right pattern of warming, high CS models should simulate the right amount of warming. So what does that mean for the future? Right? What does the future hold? Well, it depends. Do we think that this issue with sea surface temperature patterns is due to natural variability? There's reasons to think so. This is from Leopold and Hybers 2014. Kind of running a bit short, so I'm not going to go into the details of this figure. But what it shows is that observations and proxies of spectral power of sea surface temperature proxies in the West Pacific tends to have a lot more energy at low frequencies than the CMIP5 past 1000 last millennium simulations. So there's evidence in the proxy record that there's missing low frequency variability in the climate models. So if this is natural variability, what does the future hold? We've been in a negative trend of DIPO. What happens when this trend reverses, if it reverses, if this is a transient? Well, you can squint at this interval from 2014 to 2020, and you can make some inferences there. This is a temperature pattern in the observations 1917-2014 from a paper that Norm Loeb led in 2020, where we looked at the difference between the hiatus and the post-hiatus interval. SST difference 2014-2017 minus 2001-2014. So there's already a sign that the sea surface temperature pattern has switched signs. Regions that were cooling are now warming a lot more than average. So if you look at the radiative feedbacks, those also appear to have switched signs. These are the CMIP6 AMIP runs, those 9 runs, 1979-2014, negative feedbacks in the East Pacific, but in this post-hiatus minus hiatus world, 2014-2017, there's now positive feedbacks in the East Pacific. This is simulations, so it's not a pattern, you switch the sign of the feedback, but if you look in CBAF, you also see this in observations. So there's both AMIPs and evidence from the series record that as this pattern is eventually flipping, we're going to get very positive feedbacks. It's actually quite scary. This paper concludes that most models show too little sensitivity to specific sea surface temperatures, suggesting a pattern effect that may be too weak compared to observations. So the delta lambda in series might even be stronger than in AMIP. Could it be good news? Well, it depends. If it's natural variability, then there's the potential for amplified warming in both near and long term, which I'd say is bad news. What if it's a bias in the forced pattern? What if this pattern of more warming in the warm pool is actually a response to the forcing? Well, if this is transient, such as the 2 aerosols, it's still bad news, as it's going to go away and it's going to open up some very positive feedbacks. However, if the recent pattern is indicative of future warming patterns, then we might actually end up with low climate sensitivity and a low transient climate response. That would be good news. There's some evidence that it's forced response. This is a paper from Seeger et al. 2019, where they argue that they take a Keynes-Ziebiak model on top of CMIP climatology. It reproduces the CMIP trends, 1857-2018, But if you take the same Keynes-Zbiak model with observed sea surface temperatures, then it reproduces the observed pattern. It's more warming in the West Pacific.
Hey, Christy, we might want to
well,
try and wrap up soon so we can get to some questions before the end of the hour.
Oops, sorry, Aki. I had one more slide. So going forward, what we need to understand is what is the strength of the pattern effect for a given pattern, and how will the pattern change? Is this low frequency variability? What does the long-term sea surface temperature pattern looks like? So that's it. Thank you. I'm going to leave up these salient points, and I'm happy to take any questions. So
Okay.
First time giving the talk. I'm sorry I ran a bit late.
Thanks very much, Christy. Yeah, we have a couple minutes for questions. I'm sure folks can always follow up with you by email if we don't have time, but feel free to type your questions in the chat, or you can use the raise hand feature in Zoom to ask your question out loud. That's located under the reactions pane at the bottom of the Zoom screen. So any questions for Christy? I mean, since you're showing this sort of summary here in the top, the observations in the top left, I was just wondering, are there other data sets besides the NOAA observations that you showed that might have a different impact on some of the conclusions that you drew?
There are other SST products. Over this interval, 1979, 2014, they're all pretty consistent. Mm-hmm. If you go back before the satellite era, then you start having big differences in regional SST patterns. That's also the reason why I wanted to compare the coupled models, why I wanted to compare things like the Walker Circulation Index and EIS between coupled runs and ERA, because then those are much less dependent on the SST, on having the right SST patterns. So I don't think errors in the SST reconstructions can explain this, not over the recent interval.
Okay, thanks. Clara has a question. Go ahead, Clara.
Hi, Christy. Thanks so much for your just excellent talk. Just a simple question. At the very beginning, you talked about Southern Ocean low cloud feedbacks as maybe being, behind the high ECS. And then you quickly departed from that view and took us into the tropics. And I know from Rob Will's recent submitted paper that this high latitude radiative feedbacks really maybe aren't so important for ECS. Can you just talk to this point a little bit?
Right. So Mark Zelinka has a paper 2020 where he shows that the change in the Ensemble mean climate sensitivity between CMIP5 and CMIP6 can be tied to stronger Southern Ocean cloud feedbacks. The spread in climate sensitivity within the ensembles is still tied to the tropics. So that's one view. The other view is that CMIP5 models tended to reproduce historical warming better than CMIP6 climate models. We've made the Southern Ocean feedbacks stronger, and now CMIP6 models run hot. And maybe that's right. Maybe in CMIP5 there was this compensation where the warming pattern was making the models run hot, but too weak feedbacks in the Southern Ocean being too weak made them run cold, and they kind of compensated. And maybe the scary scenario is that by fixing the Southern Ocean clouds, we've unmasked this bias. Due to the pattern effect.
Thank you.
Andreas, go ahead.
Hi, Cristian. That was a really nice talk. At the beginning, you said that if we would discard the paleoclimate data, then we get this larger range of the climate sensitivity. But perhaps we shouldn't discard the paleoclimate data. And in fact, Jiang Xu has shown recently that at least for CESM2, that high climate sensitivity model seems to be incompatible with even LGM temperature reconstructions. So, perhaps not all hope is lost if we also consider the paleoclimate data.
I agree 100%. That was just the reason I said discard the paleo data was just to sort of highlight the point that the historical record can't constrain ECS. I agree 100% that the paleo record is likely the best. Well, 100% that it's likely. I agree that the paleo record is likely our strongest constraint on high climate sensitivity. So yeah, no, I don't say discard the paleo record. And Jiang Zhu's paper does a good job of showing that high climate sensitivity models also don't reproduce the paleo record. However, there is a caveat there as well, which is we need to trust the SST patterns from the paleo reconstructions if we're going to be testing these models in the paleo. They were actually funded. Jess Tierney, Kyle Armour, Greg Hakem, Natalie Burles, Dan Amrine, and I are funded by NSFP to C2 to actually look at whether there's a pattern effect at play at the LGM. And actually I see a comment by Jiang Xu. The Pliocene, a past warm climate, seems to show more warming of the eastern equatorial Pacific. Right, so if you study the Pliocene, this is very scary because it says that you can get a very warm Pliocene just because you warm in the right regions in the East Pacific, and that amplifies climate sensitivity. So yes, the paleo record offers a great opportunity to constrain climate sensitivity, but it's not entirely safe from these pattern effect considerations.
Thanks. And also, I think maybe we need also a call to the models to perform these paleoclimate simulations, in addition to the forcing simulations that you mentioned, in order to be able to test them with the paleo data.
I agree. Also, Green's function model intercomparison project. So Brian has a great question. Is there any good reason to hope that SST patterns in historical simulations will improve with eddy permitting ocean models? There is reason to think that. We know that there's issues in the coupling in the models that have to do with things like, this is one of my favorite papers, Coates and Karnauskas 2018. So there's issues with things like the strength of the equatorial undercurrent and the coupling of the surface wind stress to the equatorial undercurrent. So there to think that better resolved ocean processes, particularly in the equatorial Pacific, could improve this. There's all sorts of other potential problems, including pathways between the equatorial Pacific and the Southern Ocean, response to aerosols. There's a whole slew of possible issues in coupled models, but eddy permitting ocean models would obviously be a good first step.
Great, and then related to the previous question, Jiang put a comment in the chat as well as a link to another paper. So thanks for that. I'm not seeing any other questions. We're a bit over, so I think we'll have to wrap up. Thanks so much, Christy. Next week, everybody, just to let you know, we're going to be at a different time than our usual 11 a.m. Mountain. We're going to have Claire Monteleone from CU Boulder joining us, and to accommodate her teaching schedule, we're going to be meeting from 3 to 4 p.m. Mountain time. So